So, good morning, everybody. Can you hear me? So this session I was planning to make is about basic NSO architecture, so that anybody that's been using NSO for a year or so, you don't need this. But it's just to refresh all the terms and terminology around these components inside NSO and around, and also give you an ample opportunity to ask questions about what the architecture is, what is it that we really mean when we say things. So please, make this interactive, if you please. Raise your hand and I'll give you the word, okay? So what I want to talk about is a little bit, what is NSO really all about? What is it that it brings to organizations? It's a lot about automation, and automation in the software world means APIs. So I want to talk a little bit about what those APIs are. There are a couple of terms that we talk about all the time. It's called Stateful Convergence, and the FastMap, or sometimes Reactive FastMap. So I want to explain what those concepts really are. And then just go through a summary slide at the end to say, here are all the benefits, and here are all the reasons why you don't want to use NSO. Okay? Nodding will not sound on the film, please. Yep, I want this interactive. Sometimes I will stop and I will refuse to continue unless you acknowledge that you're with me. A couple of years back, SDN was the biggest thing that everybody was talking about, right? Software-defined networking. As it happened, just as the SDN movement was doing its thing, we just realized, oh, actually we're doing that, but we didn't know it was called SDN. And the architecture that we had in the NSO product was pretty much the same or very similar to what you had in the SDN movement. And it still plays, the SDN hype has maybe diminished a bit, but this architecture for going software in the networks is still very much with us. And this slide in the middle, in the frame here, is coming from the SDN architects, Martin Casado, Schenker, Kapanen, and those guys. And they described SDN as being a three-layered architecture. Everybody was thinking, at the time at least, about OpenFlow. You said SDN, you meant OpenFlow. No, it's a three-layer architecture for network management. And in the middle, you have this network operating system in yellow. That's really a component that abstracts all of the network and gives you an API to touch anything, anywhere in a nice and clean way. Below that, you have the forwarding layer, and that's where the OpenFlow plays, if you want to use that. There are many other competing technologies. And many other competing technologies playing on the forwarding layer. And on the top, you have a sort of abstract view, abstract network view, something that's on a higher level than the network itself. That's where you find what we call services. So what is NSO all about then? It's some people use NSO for device automation. I mean, you have scripts today, and you want to use something that can do operations towards devices, or sometimes a large set of devices, so you can script towards NSO instead and make those scripts a lot easier and simpler and more reliable. You can use it as a network operating system. Basically, it's a place, it's an application that you install in your network that gives you the ability to write applications on top of this network operating system. Just like you have the old traditional desktop operating system that treats, isolates or abstracts disks and screen, memory, whatever it is, and gives you nice clean APIs to allocate resources out of that in a nice way. You can use the network operating system to do things on your network in much the same way. And also, NSO is also used in many orchestration scenarios, basically when you have complex setups, complex services in your network that needs to do this here, then that there, and then tie it all together and maybe react to things that are happening in your network. That's what an orchestrator does. So all of those three things is what you use NSO for. Some of the recent trends in the networking industry is that, okay, we need to be more agile. We need to provide services faster. The time to market is an important thing here. We need agility, we need DevOps, we need SDN, we need network function virtualization, we need new kinds of services. So that's a key corner component for being in business in the networking industry today. We have customers that are getting used to the button. Yeah, I want this service. You go to the web portal and you say, yeah, I want to buy it, and then you expect it delivered within the next 5 minutes. The time where you can impress somebody with saying, yeah, we will deliver this to you in 3 weeks, is not impressing. And you have a lot of, everything is in the cloud, you have a lot of virtualization talk going on, maybe more talk than actual running, but it's something that you need to have in your mix. You need to be able to move some of your services from physical to virtual, and then manage the hybrid. So what we see now is a lot of talk now about speed and agility. Lower OpEx, lower operations cost is something that we traditionally saw a lot, but now more and more we see speed and agility and the ability to generate new revenue, basically being able to create new services, to adapt existing services to new conditions as being more important than lowering OpEx, even though lowering OpEx is an old driver that we always had when it comes to NSO. So what does this mean for users of NSO then? Well, you have people, you have processes, you have technology, and for the people, we need to get from the situation where a lot of people are now, where there's a team for this, and a team for that, and a team for this other thing, and they don't talk much to each other. And we need a lot more cross-functional skills, and especially cross-functional between networks and software. That's where the DevOps thing comes in. You have people in software, you have people in networks, and traditionally they have not really understood each other very well. Now we want something more in the middle, some people that can understand some of both. The more, the better, perhaps. You don't need everybody in the team to be a fully network architect, and everybody needs to be also a software designer. But you need to have some sort of ability, and you need some software expert and some network expert in the team. And you need to go from this sort of waterfall, plan everything out in the beginning of the project. You know exactly what's going to happen to your network. And then you give it to the next team that will do its part into this more agile thing. If you want to be agile in your organization, the teams have to be agile as well. And then we have the technology. A lot of the technology out there today consists of scripts and quite purpose-built systems that are doing one thing, and they do that well or not so well, and especially if you want to be agile, they don't flex that much. So you have to have something that's more like a platform, an operating system that understands any possible application that you may want to have. And then you just write a small application on top of that that decides, this is the policy today, and this is my other product that I want to launch. As making that piece much smaller and the framework much larger. That's the way to get to flexibility and agility. Just to give you a feel, since this is an introduction to what NSO is, some sort of customer snapshots. We are, of course, in the telecom operator space a lot. But we are also in the sort of virtualization or data centers and clouds scenarios. Cisco and TLF was selected as #1 SDN NFV orchestration software vendor last year by some IHS market analyst. And it's going pretty well for us. Now we are inside Cisco since 3 years back. And the number of customers and expansions and new partners that we acquire it's a nice place to be. One of the terms I'm talking about a lot here is DevOps. So what is DevOps? Well, it's when you have people and teams that are part developers and part operations people, and that operate in a sort of agile fashion. And agile means, in this case, that you don't have a fixed project plan day one, which with all these 16 steps, this is what we delivered and hand it over to the next team. But rather, you deliver in increments. You deliver a small kind of, a basic kind of service, the first iteration. Then you extend it over time with more and more functionality. And it's not known at the first iteration exactly which sequence and what functionality will be delivered in the iterations 5 and 6. We may know what we deliver in 1 and probably what we will deliver in number 2, but not 5, 6, or number 10. That is something that you see over time. What is hard, what works well, what customers want over time. And in this DevOps spiral, you have these phases with release. You release a new software, you configure it, you monitor that it's working. Then, based on what you saw, you plan the next iteration. You create that code, you verify that it works, and you package it up for the next release. And you go around this loop for every pretty short release iteration. There will be a talk later today, about the DevOps and how that applies, with the tools and the processes that you do for that. And Siri will hold that for you. So what about automation and APIs? I had to bring in this slide. It's from Cisco BTA, one of the business organizations inside Cisco, that is evaluating. They are building up business cases to help customers to motivate purchases internally. But this is the sort of summary that they brought for Cisco internal for our purposes here. And seeing that the return on investment on these projects, they vary between 88 and 738%. 88, of course, return on investment lower than 100 is not so great, but even, I mean, the worst projects return almost all that money within these 12 months. So some projects, they may have to wait a little bit more than 12 months in order to reach 100% payback. But even so, I think these are quite impressive numbers. Lowest 88% in 12 months, and several 100%. And the improvements in operational efficiency and all of those things. This is pretty fluffy stuff, so I will leave that for the sales and marketing people. But APIs, this is what the picture looked like. You have this big OSS or ITIL or order management systems on the top, and then you need to deliver the services that somebody ordered. And then you have a network on the bottom that is going to deliver the actual, but then you need a system in between that can translate the order into what do I need the network to do today. And when I talk about an API, this is the API I'm talking about. The API for this order management system to order something into the resources of the network, what's called a resource-facing service. With NSO, it's a lot about this API. We want to call it, this is a well-defined API. Even with the script, it's a sort of API. The script is doing something to the network, and obviously that is a kind of API it is using. But it's not what I would call a well-defined API. So I will explain now what I mean by well-defined and how I claim that the NSO API to the network is a well-defined API. So you have to forgive me if this becomes a little bit computer science terminology list, but okay. So well-defined, of course, well-defined means that something is properly designed as opposed to being ad hoc, something that just appeared from whatever you had. Scripts are typically very much ad hoc. You have something in the network, and that's what you try to use, and something will come out of it. But if you try to design something, you have a designer thought about what you want things to look like. There are some aspects, some properties that you want to get in there. Another thing in well-defined is also unambiguous. You want things to be clearly defined. This is what happens, and this is how it happens, as opposed to being undefined or something that let's try it and see what happens. Also accurately described so that you can read about it. You can read what will happen when you execute this API. And of course, clean and distinct so that you can understand what these functions do, and they don't overlap with 5 others that do sort of the same thing, but slightly differently or something. Or that they sometimes do this and sometimes they don't. Another term that we use with our APIs is concise. Concise means that something needs to be fairly small. You can express it in not too many words. We see a lot of APIs that even, I mean, especially those auto-generated APIs. You take a model of some kind, description of all the commands or something, and then you generate an API, and you get 600 or 60,000 function calls that you can make. That is not something that you will typically learn easily. Instead, you want these to be concise and sort of have a grammar, just like an ordinary language has. You can combine. You will say, fetch, me, and apple, and it has 3 parts. And if you remember from school, all the subject, predicate, and so on, these are the sort of things. You build things together in a natural form, rather than having a catalog, you know, those old phone books, with page up and page down of all the calls that are manipulating certain combinations of elements in the network. That is not flexible and agile. And we have model-driven. It saves you a lot of effort, and things become much clearer, and they work the same all over the place if they are model-driven. Model-driven means that you describe something using a modeling language. You describe what a car looks like. You describe what an API looks like. You describe something in this model, and then everything is derived from this model. All the API calls are, this model might describe all the nouns or verbs in your language. And then everything is just a matter of combining these nouns and verbs in that way. Model-driven also implies that there is something that is driving, so there is an engine that is driving the API and driving the operations in it. And model-driven also means that it's structured. It's followed the system, the API in this case, is following the model. Everything in the model behaves the same because we have an engine that is driving it in a structured fashion. There's not, oh, over here it works like this, and over there it works in another way because those calls were made by another team. And one of my real favorites here is transactional. Transactions is an old term dating back into the 80s, really, when it comes to databases and all those things. And something happened in the 80s. Suddenly, applications that were business applications that were written towards this transactional, suddenly, interface, they started to be, and it was all standardized with the SQL language, query language. So suddenly, these applications standardized, and they were suddenly starting to evolve very rapidly, because they could use the standard API, the standard abstraction level. Business applications before then, they were always tied to a specific database, and the abstractions in that particular one, the calls in there. Suddenly, there was a boom of business applications coming out. And now we want to do the same thing in the networking. Transactions is something that is nice for application developers, because it's making the API easy to consume. You make a call, and either it happened or it didn't. That's the first atomicity principle. It's all or nothing. You make something, you ask for something, and either it completes or you forget about it, nothing happened. And that is a trait that we as network people, we have longed for a long time. We have scripts, we have applications that are trying to do things to our network, but there's always a risk that something goes wrong in the network. So in a mature script or application, more than half of the code is devoted to detecting and cleaning up after such errors. It's a total waste of resources. Somebody else should do that. We also have this consistency requirement in a transaction. So this is from the textbook definition of what a transaction is. Anything that fulfills these 4 criteria is a transaction by definition. It doesn't have to deal with computers at all. It can be something that we define how we treat each other in this room if we wanted to. It would be a transactional mechanism. But okay, consistency. One of the many things consistency means is that whatever you put into a transaction is happening at once. There's no internal sequence or time inside the transaction. I ask you, can you do this? And the system will do just that. And it doesn't care about if I said do A and do B, or if I said do B, do A. It's the same thing. I'm asking you to do this, and the system will respond yes or no, and just do it or don't. We also have this with independence. So if you're running multiple transactions towards a transaction management system at the same time, it will appear always as there's a particular time sequence that they were invoked with. This one was happening first, and then this one. So if they overlap in time, the system will make sure it still appeared as they were running one after the other. And durable, done is done. So that means that anything that you received an OK on sticks. The system will not change its mind. It will not do something else. It will not modify your orders. It will do what you said until you say something else. You are the general of your system. You give the orders. You say march this way, and the system will march that way. There's no changing. Done is done. It's durable. It's fixed. We know what you said. With these properties in your management system, you offload the applications by a lot. I'll show you some pictures of that. This is a cornerstone in a good, well-designed API. Here's our block diagram showing what the NSO product looks like on a pretty high level. We have this NSO in gray here. You have the service manager and the device manager on the left. That corresponds to those layers you saw in the first slide with the SDN architecture. You have this service level, a high-level abstraction of what the network is doing. Then you have the device manager, which is showing a sort of concrete, everything that exists on the network element is something that you would see in the device manager. And then you have the adaptation towards the devices in this device abstraction with the NEDs that really touches down into the forwarding layer. There is a database inside NSO. It's called CDB. It used to be the configuration database, but it's holding a lot of other things than configuration these days, so I don't know. We'll have to come up with some other definition of what C means. The cool database, maybe. There's a package manager, which is a crucial thing, because what you do on top of NSO, as I said, is a sort of an application environment, an operating system, network operating system. So you run applications on top of it. And the package manager is the one that is loading and unloading and loading new versions of applications as you go, as you run. So that is a key component. And as you will see, having a lot of different components is a key feature of NSO. You have not just one application, you will have dozens. There's also, just to make sure that everybody gets it, when NSO is managing devices in the network, NSO doesn't really care at all what sort of device that is. If it's a virtual or physical, if it's local or remote, if it's layer 1, 2, 3, 4, 5, 7, if it is it's vendor A or vendor B or vendor C, if it's CLI, netconf, SNMP, we don't care. It's just a device. But just to point out that, yes, certainly we play in this virtual league. We'll just put in this ESC component. ESC is the Elastic Services Controller, which is, in NSO's eyes, is just one device. Devices doesn't have to be what you have as a traditional, you put it into the racks. It can be anything. It can be a piece of software, as in this case. It's a server. So there's nothing special about ESC per se, but we put it on this slide just to make sure that everybody gets it. Yeah, it's also doing the virtual things. It's virtual or physical, and most of all, hybrid. We don't really care if it is virtual or physical, so to us, it's just devices. I didn't mention what NEDs stand for, but it's Network Element Drivers, and it's a piece of software that adapts to whatever the device that you're managing is talking, for example, CLI or netconf or something, and keeps track of what Yang models you have in there, as you will see. Yes? It can hold operational data, for example, state of things. And, I mean, if you have a device out there in the network and it's counting the number of packets it's passing, that's state data, right? We don't want to keep that state data in CDB. That would be a waste of resources to keep updating that all the time. But there's other state that you might want to keep in CDB. For example, when you have reserved resources, I have allocated these 50 IP addresses. That is not something that is in the orders coming from the general, so it's not configuration. But it is state about what these packages are doing and dealing with. So if you are writing an allocator, for example, you would store such state in CDB as well. It may also be, for example, notifications and alarms coming in. They need to be stored somewhere. They're not configuration either. but they need to be stored somewhere. They could be stored in CDB. Good question. Like it. Anybody else ask something? So this package manager, it's dealing with, as I said, an installation, updating, uninstalling. It's keeping track of versioning quite exactly, and it keeps track of dependencies between packages. So it knows this package needs this other package, and it also needs this particular version of it. And it will refuse to load this other package unless you can fulfill this. It also isolates packages from each other so that you know that this package is not going to clobber something in there. So it's good to have this package manager so that you can upgrade and deploy these packages in runtime as the system is going. I would say it's a key feature, actually, of NSO to be able to track and handle all of these applications as separate entities. You often see stacks of applications, stacks of packages that collaborate to implement a particular use case. On the bottom, you might see several different NEDs, the network element drivers that are capable to talk into Cisco IIS, Junos, or an assurance system. And on top of that, you might have the service packages that are implementing, for example, a topology and a VPN service. And on top of that, you have something that's even higher, that's building a customer package, customer service, that is composed of, well, some VPN, but also maybe need some topology services to implement its functionality. And there might be an inventory system integration to some other system externally so that you can read and write towards that inventory. And on top of all of this, you might have a customer portal with a graphical interface that is using all of these other lower packages to do its thing. So this is maybe a particular use case might have these 6, 7 packages. But if you have several different use cases, you might end up with 50 packages. And being able to replace and upgrade these things individually is important. So granular, being able to build granular packages is key here. These packages, they can be things that you have developed yourself as an organization. They can be open source. There's a bunch of packages available as open source for NSO. Or you can purchase them either as ready-made, shrink-wrapped things that you just buy from some certain vendors, or as, let's say, some integrator is writing them for you. You see this term Yang on the top of all of these. That is the API definition. That's the model. We are dealing with Yang models. So everything in NSO revolves around Yang models. Yang models describe what you can configure within this subsystem, which can be a device, or it can be a service, or whatever it is. It's what you can configure, the operational state that you want to, this package wants to expose to its customers, what actions you can execute on it, in terms of, maybe if this is a NED, maybe you want this device to ping somebody, so then you can run an action to ping, or to clear its counters, or whatever it may be, and whatever notifications that can be received from this package, alarms or notifications, I'm ready, I've done what you asked me to now, or whatever it is. So all of these things are described in this Yang model. So every package will have a Yang model, more or less anyway, that describes what you can do with this package. This is the interface that you can leverage when you are using this package. And it's model-driven, so it behaves all the same. Just you understand the Yang model, you know what you can do with this package. With NSO, these Yang models is what is used for rendering all the management interfaces. So you get a command line interface, you get a web UI, you get all the programmatic APIs in Java or Python or Erlang or whatever it is. They are derived from and rendered in runtime based on this Yang model. And what does render mean now? Render means to show an image of something. So whenever you log into the CLI and you try to show something, it is rendering that image at that instant. We are not doing Yang and then taking all the Yang files and generating some megalonic code piece or something like that. It is rendering these things in runtime. The web UI is not something you can read about. Show me the HTML here. The HTML is being rendered in runtime. It's being computed as you speak. Oh, you want to see that? Yeah, let me figure out how that looks. It looks like this. And that's very important because when you are working with these network devices, they have very, very large models. If you wanted to generate code for all of those models with API calls for everything in there, you would have trouble to load it even on a laptop like this. It becomes very, very large. These Yang models are not only used for the northbound interfaces towards the operators and applications, but they are also used for the database. So the database, these Yang models is the database schema. So as soon as you load a Yang model that contains, you can configure this and you can view that, that's automatically added to the database schema, so it knows what to do. The Yang models are the schema. And these Yang models are also used to derive how do I talk to a device in the NEDs here? What commands should I send to it? For CLI devices and other non-transactional devices, it will figure out things. The Yang model contains information about which sequence do I need to do this. I need to send this command first and that command later, because in a non-transactional world, you have to worry about such things. Make sense? Any comments or questions, additions? I'm not giving up. You have to ask something. Come on. I'm not giving in. If you want to hear the second half of this presentation, come on now.
So Jan, can you talk about the wrappers, like around Yang, like Netcon, REST, Yang, as you said, it's a data model. What other protocols you need to communicate, right?
Yeah, I mean, you have these northbound interfaces here, and some of them are meant for humans, like the CLI and the Web UI. Others are meant for programmers, APIs basically. So they are available in many different languages, like there's a Java API, there's a Python API, there's even a C API, it's not official, and there's an Erlang API. So you can write applications in all these languages. And if you write a package in one language, it can of course use the functionality of another package, regardless of what language that one is written in, because it has a Yang API. And Yang has a representation in all of these different languages. If you have some particular favorite language that you like, let us know, and we can think about how to integrate that into the mix too. Thank you. Any other comments, questions? You passed the test. Okay, I'll go on. The next topic I want to talk about is stateful convergence. How many of you have heard this term before? Okay, some. And we have this reactive or FastMap or reactive FastMap concepts. What are they? They are key cornerstones for why NSO is so useful. I'll explain. So if we start with this, I mean, it's all about how do you translate the service level information. Service level information is about, okay, let's see, I want to configure a VPN. So I have a few attributes on the VPN, like 5 or 10 things that I might want to configure. And then that needs to be translated into, well, which devices do I need and where are they and what model are they, I mean, what vendor do they come from? It's a Cisco or it's Juniper or it's an Arista, whatever. And what do I need to do to each of those? So there's lots and lots of parameters on the detailed network level, maybe hundreds or maybe thousands of things that need to be touched on the devices in the network. So you have this small number of things on the top, on the service level, that needs to be translated by an application into something concrete on the network level. And to do this on the network level, sometimes that can be pretty easy. I mean, you have to have a simple use case, maybe translating a VPN from the service level to the device level is something, you just do this, you push it out, and that's it. But in many cases, there are intermediate steps. Like, for example, I need to allocate a free IP address, or a route distinguisher, or route target, or whatever it is called. I'm not a networking guy, I don't know these things. Anyway, you need to allocate things in there. Maybe you need to spin up a virtual machine. I mean, this service is with a firewall. I need to spin up a firewall and make sure that all the traffic goes through it. These more complicated services that have several stages, I mean to spin up a virtual machine, and I'm not going to sit here and wait So I'm going to say, okay, do that, tell me when you're done, come back and we will continue the delivery process at a later time. This is, I mean, a lot of people would implement this as a workflow with step 8, step 1, step B, step 2, step 3, step 4, and so on, until, and in some cases I programmed, I think we were up to 26 stages for one service. But the problem is that sometimes when you are at step 14 in this process, things change. Sometimes the data center that you were using to deploy that virtual machine went down and is no longer accessible. Or the customer changed his mind, and now he just launched this process 2 minutes ago, but now he wants more bandwidth in the middle of things. What do you do? With the workflow definition of your service, things become pretty complicated when things change in the middle. There is not many arrows that go back and forth between all the bubbles to resolve these cases. And if there are, that's even worse, because then you have every bubble arrow to every other bubble kind of diagram. How do you develop that? And even worse, how do you test it? It is horrible. And that is where all these workflow solutions die, when they encounter reality. When all these dirty use cases come up. Oh, you want to be able to change this in the fly? Oh, there can be errors in the network. It all looks very nice on this. Yeah, how McDonald's delivers a hamburger to a customer. It has 5 steps, and you do it, but things can go wrong in every step, and that's never shown in these diagrams. So what do you do then? That is where the stateful convergence comes in. Stateful convergence means that instead of defining this as a sort of workflow, it is kind of workflow-like, but there's one major difference here, is you define these steps as sort of a direction. You want the system to work towards that way. You want to reach the end goal, stage number 26. But you acknowledge that the system can go back and forth between these in any direction all the time. Oh, I went from stage 14 to 15, but now this happens, I'm back to 6. Of course, I have to understand what I did now, because I did set up something to that data center over there, which is now all wrong. So I have to undo that in order to get back to 6, and then retrace it from 7 and on. And that is all what stateful convergence is. We want to converge on the final stage. And then figure out how to navigate all the steps in between, and sometimes backtrack and undo what we did, and then retrack again until we reach the goal. And actually, with stateful convergence, in many cases, there is no end of it. It's always ongoing to converge to the end goal. Because even if you reach the end goal, suddenly something can go wrong. Oh, we lost that connection. That VM went down. The customer changed his mind, whatever it is. And then we have to do the same thing again. You just have to backtrack to something, respin it in some other way, and reach the goal again. So many services, many people that are delivering services like this, they have a stateful convergence process that goes on forever. Every service is always trying to reach the end goal. Some of them are there, but may not be there for long. And they've thrown away. After 6 months of being deployed, something happened, boom, oh, now we have to retrace here and try it again. So that's the difference between stateful convergence and a workflow. And NSO is actually very good at this. Stateful convergence is at the heart of it, because the difficult thing in a workflow system is that you have to think about all possible arrows and all possible actions that you have to take from every bubble, and that's a lot. When you draw the first sequence diagram with 5 states, it's not a lot, but as you add all the errors and complexity that might happen at any time, it grows exponentially with the number of states. It's unmanageable. So what NSO is doing, it is basically doing this, but it's computing all of these things back and forth, what you need to do. Oh, to go from stage 17 with this particular setup back to stage 6, this is how you do it. You deallocate these things, you allocate a new route from here to there, and it's doing all of that without you having to do a lot of programming. And that's where this FastMap is coming in. Yes?
Is it the same as the rollback function that NSO?
I would not say. Rollback is a highly overloaded term. People use it in many different ways. In NSO, we call rollback the action when an operator says, no, I did this, and it's up and running, but I don't like it anymore. I want to roll back to what it was like yesterday at noon. That is a rollback. It's an operator-initiated action to go back to a previous configuration. So that is not at all to do with this. even though that rollback operation is also using this FastMap capability that I'm coming to now. So it is based on the same fundamental technology, yes, but that term is not something I would use for this. But I like your question, that's excellent.
But then, in every net that you're writing, you have to define an opposite command to every command that configures something. You have to define an under step, right? So I don't really see how you workflow otherwise.
It's an excellent question, and I have a presentation on NEDs tomorrow. Come to that one, and I'll explain all about how NEDs do this. But the short answer is no. I mean, yes, of course. Every NED needs to be able to convey, this is the configuration I want you to have, no matter what it was before. So it needs to know what it wants the device to have, and it needs to know how to navigate from wherever the device is to that one. So in that sense, yes, of course. But it doesn't need to have an explicit list that this is how you do it, and this is how you undo it. No, that's not how it works. Coming to that now, excellent question. Prompt for me. Thanks. So if you look at a traditional sort of network management system, you can see it has a front end. It has a web UI typically, and maybe some REST API or something like that, right, on the top. Then it has a layer of business logic that really understands what this NMS is doing, like, for example, provisioning VPNs. So it understands what the VPN is, how to calculate which devices to actually use, and compute a path between them and stuff like that. The interesting part, the thing that you care about. Then, as I said, according to numbers I got from Nokia Siemens and from my own experience, I can say that in a mature NMS that actually works in the real world, half of the code flow is about error handling. It's about detecting, oh, we went wrong here, and trying to figure out what to do about it. Undoing whatever it already did, and putting things back into order again. If you count the amount of dollars you have to invest, I think it's even worse, because that is, the error handling code is the more expensive code. It's the difficult code to write, and to get right, and to test. How do you test all of these error conditions? It is difficult and expensive. So in a traditional NMS system, you are spending a lot of dollars on that part if you want it to work well. And on the back end then, towards the network, you typically have some sort of templates or CLI scripts or whatever, SNMP, PDUs you are sending out. So you have to encode all the operations that this NMS wants to do to the network in terms of something that it can run, invoke this procedure towards the network. So that's a traditional view of what an NMS does. Now, I'm talking here all along about, okay, NSO wants to make you agile. So how can we make you succeed in implementing services quickly and easily with much less code? That is the key, right? You have to be able to express what you are interested in doing with your network in much less code. That's the key. How do you do that? Well, I claim the picture is something like this. For you, when you want to implement a service, yes, you have to define the Yang model for it, basically the interface to the outside world, to the customer, to the CLI or web UI, and to other applications sitting on top of you. You have to define, what can I configure on your VPN? What actions can I execute? Can I reset this thing? Okay, I need an action for that. Can it deliver me notifications? Can I read some stats on it? Is it up or down? Or can I give grades on how well it is performing? Whatever. You have to define those things in the Yang model. The good news is that Yang models are quick to write, and usually service models are a page or 2 or 3. They are very small. Then you also have to define the business logic. You have to talk to some network expert that understands, oh, in order to provision this particular kind of VPN, I need to set up this on this kind of device, and if you have a Juniper device, it's going to work like this instead, and all of these things. So somebody needs to understand, how do I represent my idea of a service on the network? When you ask somebody, describe me how your service works, they will invariably tell you how to create that service from scratch. They will always say, I just asked the question openly, remember? I said, describe how your service works. That was my question. But the answer I will get back is how to create it. But I also need to be able to delete it, right? And I also need to be able to modify something that's already up and running. Yeah, the customer has this running right now. With minimal disruption, I want to change the bandwidth to twice as much. I don't want to tear it down 10 minutes and then it's new one. I would want to be able to modify this. But actually, there's a lot of code in the traditional NMS for being able to delete, and even more, the worst one, to modify. There is so many ways. If you have a service with 20 parameters, you have sort of like 2 to the power of 20 number of ways that you can modify it, right? It's horrible. How many ways can you modify a service? Basically infinite. So if you have to code up all of those different change cases, you die from no food from your customers. So that's why most of these traditional NMSs, they don't. They specify, you can change it in these 3 ways with this particular screens. Okay, that's it. But in the NSO way, what you have to do, you have to create, to implement this create function, but not the delete and not the modify. So, and you don't need to worry about the error handling because we have transactions, right? It's either happening completely, or if something is not working out all right, it's NSO's problem to make sure it's gone. You don't, as an application writer, as a service implementer, you don't have to worry about it. You don't have to implement this back-end scripts towards the network either, because that's taken care of by the NEDs and the YANG and all these things. You just need to say, I want this parameter to be 14, and then NSO will take care of that. Either it is 14 or the whole thing didn't happen. And also you have this northbound part. You don't need to worry about implementing interfaces for humans or for other applications sitting on top of you, because that is just derived from the YANG model automatically. So the amount of code that you have to write when you're writing your network applications is tremendously much smaller. So how is this possible? Well, the keyword here is something called FastMap, and I'll briefly explain how it works, so just to get an idea. Okay, so we say, okay, we have this create function that creates a service on the network. You say, I want a VPN, you supply 20 parameters to it, and say, here, go. Then they're inside the service package, something needs to receive those 20 parameters and define what to do on the network. It gets these parameters, these 20 parameters, through the NSO APIs. Read this, read that from the database. So it is a nice and clean API to get the input data. It's also writing to the network using that same sort of clean API, NSO API. Write this, set this one to 14, allocate one of these, create one of those interfaces here. It's just using a transactional database-like API for that, no scripting or anything like that. And then it's done. What happens in NSO then is that, of course, those changes that were written using the NSO API, NSO can compare with whatever you have in the database and figure out what is the actual diff. Maybe this service wrote a few things that were already in the network. We don't care about them. Only the diff is what we write to the network. And also, we record that diff, or actually the inverse of that diff. NSO is if I say, the heart of NSO really is the transaction manager. It can do anything you can imagine with transactions. And computing, just like you can compute the forward diff to something, it can also just as easily, by switching to arguments in the function, compute the backwards diff for going from that back to what you had. So, and this undo information for keeping track of what you need to do to undo this service is saved in the database together with the service. Okay, so what about delete then? Well, that was easy because NSO doesn't need to involve your code at all. It has the undo information already in there. So when the customer wants to delete the service, it just replaces this information about what to undo and pushes the diff to the network. It's gone. No code from your part. So what about the trickiest case of them all, that's the modify? Well, what NSO does, it is giving you, it is first doing the sort of thing you didn't delete. It's removing the service entirely in memory. It's not sending this to the network. It's removing the service by playing this undo information in memory into your code. And now say, now go create your service as you want it to look now. And now you see, oh, this data center link is down, and I have available resources over here, so you spin it this way this time, just as you would in create. The create code is running one more time unmodified. It doesn't even need to know that this is a modified case. It can know that if it wants to, but it doesn't need to. And then it's creating a new service. Of course, a lot of that created configuration probably will overlap with what it was last time. Maybe it was only the bandwidth that was different. So 99% or 50% or 20% is the same. And NSO will send out the diff to the network, the actual bandwidth change if that was everything that changed. and record new undo information and store that in the service. So this way, by this mechanism, which is called FastMap patent something, we only have to implement that create function. And this is also how this stateful convergence works, because if the stateful convergence, okay, I was at stage 17, and now I need to have a resource that I don't have because it's down or something, you know, that was located in stage 6. When the create code runs again, it will run through stage 1, 2, because you're deleting the old service information. It's creating stage 1, 2, 3, 4, 5, 6. Oh, I already have all of those resources for me. But at 6, it says, no, I don't have that anymore. So then it will allocate a new resource for stage number 6 and continue with stage 7. And of course, when you get to that stage number 6, there will be a lot of things that have been pushed out to the network for stages 8, 9, 10, 14, 16, but they will just be removed by the diff, by NSO. So your create code doesn't even know. You get stateful convergence for free. Kind of nice. It's a lot of work to do that manually.
And yeah, there is a dependency on the net as well, right? For example, if network needs to modify something, if network needs to undo and then apply that.
I would say that for this level of discussion, there's no dependency on the NED whatsoever. When it comes to practical NED wanting to convey a particular, this is the configuration you should have, Mr. Device, well, sometimes there are some complications in there, but it's totally separate discussion from this. But strange things may happen at that layer, and I'll talk about that tomorrow. But for this FastMap discussion, you don't need to worry about the NEDs at all.
What's the, when you do the rollback 17 what's the overhead
It depends on how you wrote your service code. But generally speaking, it is very small. And we're talking about micro or milliseconds. So it's something, the time you spend in the server to compute these things is several orders of magnitude less than it was anything that involves network equipment, right? 1,000 times faster or 1,000,000 times faster than talking to anything that involves network equipment. Of course, there is sort of overhead in there. I shouldn't say that there isn't. This sort of mechanism computes things that we have already computed. But it's saving a lot of coding for handling all of those different cases that might arise otherwise. So it is, for the purposes that we want to achieve here, agility, we are wasting a few microseconds or milliseconds of CPU power time in order to make a nice and simple programming model. That's the trade-off. So I talked about FastMap, and reactive FastMap is really these stages, the name that we have for when a service is being invoked over and over again to recompute to get to a further state. A FastMap service is basically just has this one stage. It does everything at once. And as soon as it has more than one stage, that's what we call a reactive FastMap service. So I think I've said all of this already, really. But anyway, this is what makes NSO services able to react to changes in the environment. For example, a link went down, or the customer changed his mind, or whatever it is. But by just running the same create code again, no difference. And then NSO will figure out what to do on the network and into the database to make this happen. And I think we're just on time here. The summary slide. Yes?
I have a question regarding the reactive process.
Yeah, okay.
Here, the changes in the network are the changes that happen in the lane zone or in noise load or something. Is it reflected on the NSO itself, receives notification, which require a third party, of course, that will talk to the NSO, will receive the trigger, or can it also be introduced? Do you know what?
Not completely. The question was, yeah.
Condition happens between router 1 and router 2.
Yes.
And this condition requires, for example, another configuration or rerouting traffic or something. So this condition will be seen by the NSO,
Yeah, excellent question, actually. I mean, if you are encoding your create method in such a way that it is checking the loads and availability of all the links, then of course the create method can do this on its own. But actually, just as you are implying, what happens most of the time is not that you encode a lot of this information in the create method, but instead that you have a monitoring system somewhere. And NSO is configuring these 3 devices in the VPN, or these 20 devices, and the monitoring system to tell the monitoring system about these 20 are forming a VPN like this. And when the monitoring is detecting that, oh, one of the links here is going down or going bad, that will trigger a recalculation, but that will trigger what we call a redeploy of the service. Can you recompute yourself in some way to avoid this problem? So that it is some other system that is being provisioned as part of the service that will react and see that, oh, the environment has changed now. Another change that NSO would detect itself is, of course, if a customer changes his mind, he wants double bandwidth right now. That's something that NSO would detect. But if the conditions in the network are changed, that is often an external agent that is redeploying the service based on information that it got from NSO in the first place. Like, which service should I redeploy when I see this issue on this link? Yeah, this service. So you have the connection back to the service by NSO information. And there's a discussion on orchestrated assurance tomorrow morning, which is talking about exactly this.
Is it a good practice to have the option that you just mentioned, the first one, where service is written in a way where it keeps on checking, and then do the redeploy if things changes, or it's a good practice to have the third system doing the monitoring and informing NSO if it changes?
I think you need both, because when you are, even if you get an alarm from an external system that something is bad on one of the links, you need, when you are calculating and allocating links here, then you need to take this information into account somehow. So it needs to do some sort of checking in the create also to see, oh, I'm not going to use that link because that one is really bad right now. So some sort of feedback is required in the create there. I think we're running out of time for this session, but I'll be here on the break. I'll just finish this off with this last slide. So with NSO, it's a lot about Yang modeling rather than coding. You're moving a lot of the effort from writing actual Python or Java code into writing a model that you can consume in a number of different ways. The database, the northbound APIs, the southbound APIs, they all consume this Yang model. And this is what you can give to your customers. This is how you consume my service. The whole of NSO is then a model-driven platform in its truest sense. Everything is based on these Yang models. Whatever you have in the Yang model is something that's accessible through the APIs. Anything else is not. It's based on transactions. The APIs are all transactional, which if you don't feel immediately, oh, this is the greatest thing I've heard today, then you should read about transactions, because that is saving you so much effort in writing these applications. And being able to compose packages, make quite small packages that are doing one thing really well, and compose them into stacks of packages in a hierarchy for a particular use case, that is a key thing. And then you have this whole thing with that stateful convergence. You don't have to work with a sort of workflow mind and all the exceptional cases. You can get from state unprovisioned to fully provisioned in 26 stages in reality, with all the possibilities of change that coming from customers or from the network events for real. So I think that is the case where we say that NSO is really helping. It tremendously accelerates your development of your custom services. Thank you.